Welcome to part 2, designing the method. And in our case, we're designing an online survey. In this part of the course, we'll talk about sampling techniques, determining sample sources and sizes, and the role effect size and power have in that process. So let's get started. Sampling can be one of the most challenging parts of the research. As a reminder, the population is the entire group for which you want to draw conclusions. And the sample is the subset of that group, and they can be hard to reach. In determining your sample method, you start by defining the sample frame. The sample frame is the source from which your sample is drawn. For example, if you select your sample from PEDRA, then your sample frame is going to be the list of PEDRA members. Coverage errors can occur when members of the population of interest are not included in that frame. For example, you might ask, are PEDRA members truly representative of your whole population, or do they represent a more engaged group within your population? So in this case, you may want to expand your frame to ensure less engaged respondents are also represented in your sample. While it is tempting to survey only those you have easy or free access to, make sure you are aware of potential biases and consider adding non-affiliated options from a more general population source. Furthermore, you can improve your sample frame by introducing random selection or a thoughtfully stratified approach, ensuring you have access to a representative mix of respondents. Depending on your objective, you may decide to include a subset of your sample from the general population through a sample provider. Sample providers have huge lists of people who represent the population as a whole, and you can target people within their lists, for example, those people with skin conditions like eczema. But naturally, these lists have certain biases associated with them as well. Most of the people on the lists have opted in, so there's a self-selection bias, and they receive an incentive to complete surveys. So you can get folks who are gaming the system and answering as many surveys as possible. Sample providers will charge you per response, and the harder it is to get those people, the more it will cost. And the length of the survey also increases your cost. The longer it is, the more expensive it will be. There are basically two types of sampling that can apply to your frame and the sample selection within your frame. The first is probability sampling. Selection is based on random criteria. So every individual has equal chance of being included in your study. If you want to produce results that are representative of the whole population, you need to use probability sampling techniques. The second is non-probability sampling. Selection is based on non-random criteria, and not every individual has a chance of being included. This is cheaper and easier, and therefore it's most common. But technically, it violates assumptions that are required for statistical inferences. Probability sampling is easier than you think. While considering your sample source, just be mindful to what extent that source can be selected randomly, meeting probability sampling criteria. For the following examples, I want you to imagine that your population of interest is the 11,000 board-certified pediatric dermatologists in the United States. Using this as an example, we're going to talk about the types of probability sampling. And the first is a simple random sample. So imagine that you have the total list of pediatric dermatologists. You have 11,000 in this list, and you want to choose a sample of 400. You could number that list and then use a random number generator to determine which of those 400 you select for your sample. In the next example, this is a systematic approach. So instead of using a random number generator, you take every nth pediatric dermatologist. For example, you take every 28th dermatologist in the list for your sample. You could also take a stratified approach. And in this case, suppose you want to have gender and geographic location represented in a specific way. So you would sort your population or your list into strata based on gender and geographic region. And then you randomly or systematically select within those groups. If, for example, you have access to a pediatric dermatology database, you can randomly select criteria such as zip code and base your selection on that. It may not be possible to get a complete list of the population you're studying, so you could take a cluster or multi-stage approach. In this case, you would randomly select among the lists that are available to you. Let's do a quick comparison of these approaches. Simple random sampling is a very robust method, and it will give you a good chance of getting a true representation of your population. But it can be tedious and time-consuming. Systematic sampling is a good alternative to a truly random approach. It really comes down to what is easier or makes more sense given those two alternatives. Stratified sampling might make more sense if you're worried about getting certain groups within your population. The most convenient probability method is using a cluster or multi-stage approach. You may not get a true representation, but it is often a good feasible alternative. Now let's look at non-probability sampling that does not include random or systematic selection. You are probably familiar with convenient sampling. It's just like it sounds. You find your sample conveniently, for example, those who are nearby or at the same conference you're attending. Another type of non-probability sampling is self-selection. For example, you send out your survey to all PEDRA members, and about 10% respond, and they've self-selected to be the respondents. Purposive sampling is where you have a very specific criteria in mind and you go looking for those people. For example, suppose you're looking for dermatologists who have used a very specific diagnostic heuristic. Another approach is using the snowball method, and this is becoming more common with social media. That is, you ask a dermatologist, for example, to refer other dermatologists to the survey. So it's a networking approach. Non-probability sampling is cheaper and easier relative to probability sampling because you survey those who are easier to reach. So when is non-probability sampling the best route? Well, in some cases, you may not have the option of doing probability sampling. For example, you may not have the money or the time, or maybe you have limited access to your population. It might also be the case that your objective is more qualitative in nature and just doesn't call for a random selected sample. Your aim might be to describe, explore, and identify, and maybe your population is homogeneous and you don't really expect a lot of variation among respondents. This cartoon is from the Cartoon Guide to Statistics, a book I highly recommend. As the cartoon suggests, in the real world, surveying randomly is difficult. For instance, surveying voters by randomly dialing telephones or telephone numbers is biased. It ignores voters without a telephone and oversamples people with more than one number. Once you have selected someone randomly to take your survey, you want to do everything you can to get them to take it. Otherwise, your sample may be biased with overrepresenting those who are not busy. Generally, a lower response rate indicates the more potential for bias. The industry standard for contacting people once they have been randomly selected is to attempt to get a hold of them to take your survey 3 to 7 times. If you have difficulty reaching them through one method, say via email, you should try other methods like phoning them or texting. So while probability sampling is generally preferred but difficult to do, you can improve your method by moving in that direction. The aim of sampling, after all, is to collect data from a few because you don't have the time, money, or need to collect data from everyone of interest. And the best way to do this is by selecting your sample randomly. So before you accept a non-probability approach, understand your potential biases and consider incorporating random selection if possible. The bottom line is most statistical methods used in survey research assume that you have done probability sampling. The models needed for non-probability sampling have not hit the mainstream yet. For more information on this topic, I recommend this 2013 report from the American Association for Public Opinion Research. Let's look at how some of these non-probability methods can get closer to a probability approach. Looking at our first example, convenience sampling, where you are asking pediatric dermatologists to answer a questionnaire at a conference. You can improve this approach by first randomly selecting the conference that you attend. You can plan on approaching all attendees and recording the refusals, or systematically interview every 10th attendee. In the self-selection example, imagine you sent surveys out to all PEDRA members but only got about 10% back. To improve this method, you could randomly select the organizations from which your sample is drawn. Another option, of course, is to send surveys to a randomized selection or a systematic nth member. Finally, you want to follow up with those you sent surveys to a certain number of times to increase response rate, and this should be detailed in your sampling plan. If you are looking for very specific respondents, you should first establish, if you can, how big that population is of those very specific respondents. From there, you can set up some sort of random selection or quota system to represent those specific respondents. If you are using a snowball or networking approach, you could do your initial selection of the dermatologists randomly and then do cluster surveys around those individuals. As part of your sampling plan, you will determine the appropriate sample size, and the tools you need to do this are readily available. You may have already determined this based on previous literature in your literature review. Another option is to use a table that gives you the appropriate sample size given the population size, margin of error, and confidence interval. Or you can calculate the size given the power you need to meet your research objective. I will cover these options in detail in the next few slides. Let's talk about what is meaningful given your objective. We will consider the study comparing treatments A and B in terms of quality of life. When we talk about the appropriate sample size for this study, we need to consider our objective. Is the objective to provide practical treatment guidelines or to determine even the slightest differences in the QOL score between these two treatments? In other words, what difference in QOL score would we consider them to be equal? Would a tiny difference in QOL score be meaningful, or are you looking for bigger differences? To answer this question, you might consider real-world variables, such as the cost of the treatments, availability, or side effects. If your objective is to detect larger differences, like the chart on the left, your sample size will be smaller. If your objective is to detect smaller differences, like the chart on the right, your sample size will be larger. Probabilistic sampling allows you to make inferences to the population given a certain amount of error and confidence. Just like in the previous example with treatment A versus treatment B, the margin of error and levels of confidence are choices you make based on what is meaningful given your objective. In this example, imagine you are measuring patient satisfaction at a clinic for each provider, assuming that each provider has roughly 2,300 patients. As a reminder, the margin of sampling error describes how close we can reasonably expect a survey result to fall relative to the true population value. A 95% confidence interval simply means out of repeated random samples, there is a 95% chance that that interval, for example, plus or minus 5% for a sample of 300, contains the true population value. Imagine in this case, you would ideally have plus or minus 5% with an N of 300 for each provider. But your budget only allows for serving 100 per provider, so you accept plus or minus 10%, even though you would be comfortable or more comfortable with a slighter margin of error. In addition to describing a population characteristic like our previous examples, you may want to make a comparison within the population, like the example with treatment A versus treatment B, or comparing distributions of dermatologic conditions across diagnosis-related groups. Comparing a distribution would require using something like a chi-square for your statistic. And in this case, you would use a tool such as G-Power to calculate the appropriate sample size. In terms of sample size, there are several tools that are available that are free and easy. Confidence interval tables, online calculators, and applications like G-Power will help you in determining the appropriate size. Calculators and applications include a few additional inputs, such as the statistics that you are using for your analysis. But a simple table will get you in the ballpark of where you need to be in terms of sample size for your survey. Another useful tool is having a good conceptual understanding of how sample size for quantitative research affects your statistics, even if you are working with a statistician. Most online surveys have a sample from around 400 to 600. That gives you plus or minus 4 to 5%. Sample is expensive, and you do reach a point of diminishing returns. If you were to double the cost and the size of your sample, let's say to an N of 1,000, you can see that you only make slight gains of 1%, so you end up with plus or minus 3.1%. You can get away with a smaller sample size if you're studying a large effect. So, for example, a big difference between QOL versus a small difference in QOL. And if you have little variation in your data, that is, you have a small standard deviation, you don't need as much sample in that case either. That is, if your sample is homogeneous, you don't have a lot of variation among respondents. And most inferential statistics assume a normal distribution, and that can't be established until you have a sample of at least 30. Up to this point, we have been talking about your overall sample size. But when you get into analysis, you may be looking at subgroups within your sample. So if you want to analyze the female population, then that N of 200 will give you roughly plus or minus 7%. You really need about an N of 100 for any subgroup of interest, and that will give you plus or minus 10%. If you're unable to get a representative sample while you are fielding your survey, you can weight the data in the analysis phase accordingly to accommodate for undersampling a particular group. You can use a combination of quotas and weighting to get just enough to study that group, for example, a quota of 100, but then use weighting to ensure that that 100 represents a true proportion of the population. Our whole sampling discussion has been around quantitative data and analysis. And as we mentioned earlier, surveys can also be qualitative in nature. So let's talk a little bit about that. Let's consider our earlier example where we had one quantitative question, how many months have you been on treatment A, followed up by a qualitative question, what has your experience been with treatment A? In general, the aim with qualitative questions is describing. You want to capture an experience, sort of a rich description. You don't need 100 people to tell you the same thing. You want to make sure you capture all the different experiences people are having. You're looking for data saturation. It's sort of the opposite of quantitative research where you're looking for redundancy. You want every count of one occurrence. In this case, you really just want one account of every occurrence. And getting to the point of data saturation will depend on the complexity and nature of what you're studying. Variation among respondents will take you longer to get there. So let's compare quantitative sampling to qualitative sampling in this very simple example. On the left, we have a big effect, a high threshold, and on the right, we have a small effect, a low threshold. And let's look at scenarios for two different populations. In our diverse population on the top there, we've got a mouse, a dog, a person, and a bird. This is a diverse sample, and you're going to see a higher standard deviation as these guys go through the door. On the bottom, we have a homogeneous sample. In this case, we're going to have a lower standard deviation. Similar people, or the same person in repeated measures, going through a door with a high threshold, you're going to see this problem pop up just about every time. They're going to trip. However, in a diverse sample, you have a mouse, dog, person, and bird going through the door, and you're probably only going to see maybe the dog and the person trip. So it's going to take more creatures going through that door to see an effect. And because we have a bigger effect on the left than we do on the right, we have a bigger threshold. It will take more creatures going through the door on the right before we see someone trip over that threshold. In the end, we'll have a result, we'll have an outcome. We will be able to tell you how many people or creatures tripped over the obstacle, and we'll have some certainty related to that and determine whether or not our results are statistically significant. Now let's look at the qualitative approach to this same problem. We have a common occurrence on the left and an uncommon occurrence on the right. Just like in the quantitative example, we're going to see data saturation pretty quickly with the homogeneous sample going through the high threshold. We're going to see the trip over and over again very quickly. In our diverse sample, it's going to take more creatures going through the door to start seeing data saturation. And with an uncommon occurrence, we will need to make more observations before we reach data saturation. But our results in this case are going to be descriptions. We simply need to record that people have tripped, dogs and mice ran over the threshold, and the bird did not encounter the threshold. It takes relatively few observations to see all the possible occurrences. This probability chart was taken from measuringusability.com, and it does a good job illustrating how small samples work in qualitative research. On the bottom, the x-axis, you have the percent of users who experience a problem, and this is applied to a usability problem, say with a website. On the y-axis, you have the probability of detecting that problem. This chart shows you what the probability is of detecting a problem given a sample size of 7 in the blue line or a sample size of 15 in the red line. Even though this probability table was designed for website usability in mind, it works for our threshold example. If in the real world 10% of the population experiences the problem, you have a 50% chance of seeing that problem or encountering that occurrence in your research with a sample size of 7, and an 80% chance of seeing that occurrence with a sample size of 15. If in the real world 70% of the population experiences the problem, for example, tripping over the threshold, you have nearly a 99% chance of seeing that occurrence with a sample size of 7 or 15. And just like in quantitative research, if you're studying subgroups or a diverse population, you may need to do a small sample within each subgroup. This concludes part 2, designing your method. In summary, be aware of bias in your sample source. If possible, randomize your sample selection. Use tools to help guide decisions about sample size while considering what results are meaningful. Consider sizes required for studying subgroups of interest. Be mindful of size requirements for qualitative versus quantitative research and questions. Keep in mind that larger sample sizes and lower standard deviations provide more power. That is, you can more easily detect effects in your research if they exist.